Okay, in this video, we're going to look at 6.8, which is all about increasing, decreasing, and piecewise functions. And so, first, just some quick examples. Okay, these three examples, we have increasing and decreasing and constant. And so what we're looking for when we say increasing is where is the function growing as x moves this way. So as x moves this way, y should be going up. That's increasing. As x moves this way, decreasing is y should be going down. It's just a very simple way of looking at increasing and decreasing. And so here, it's increasing until this point here. So all of these x values, all of those x values, y is increasing. Increase, increase, increase. But right here at this maximum value, they switch. And if you notice, these are all decreasing. So these x values increasing, these x values decreasing. In other words, for these x values, y is going up. For these x values, y is going down. Kind of the opposite happens here through this minimum point. This was a maximum point. This was a minimum point. And if I'm looking at the values on this side, these x values, and the values on this side, these x values. On this side, is y going up or going down? Well, it's going down. So y is going down. On this side, y is going up. So we have decreasing on this side and increasing on this side. And once again, we're just checking, as x is moving from left to right, what is y doing? As x is moving from left to right, y is getting bigger, so it's increase. As x is moving from left to right on this piece, the y values are getting smaller, so decrease. This side, y is getting smaller, so decrease. This side, y is getting larger, so increase. Now, if it's a perfectly flat line, then you might have guessed constant. It's not increasing, it's not moving up as x goes from left to right, it's not moving up, it's not moving down, it's just constant. And that's all we have to do for that kind of problem is we just call it constant. Okay, so kind of a subplot of this idea of increasing and decreasing, it kind of gives us the ability to talk about these places where it switches from increasing to decreasing. And those places are relative min and max. And so if I have a function that looks like this, and I'll just put the bar right here. Okay, so I've got a function that looks like this. This piece here is not the maximum of the function. Why? Well, because these values up here are larger than this y value. But it is a relative max, relative to this area here, relative to a specific area. It is a maximum, but not of the overall. So that's why it's called relative max and min versus absolute max and min. The absolute max is the highest value that we have for the function. Now, what would this then be called? The relative min. So we have a max here, we have a min here. But what do you notice about relative min and max in relationship to increasing, decreasing? And I'll do this in blue. Increase, increase, increase. Relative max, oh, decrease, decrease, decrease. Relative min, increase, increase, increase. So at these relative min-max points, what happens? The graph changes from increasing to decreasing or vice versa. Changes from increasing to decreasing or decreasing to increasing. So at these positions, you can see that it flips from increasing to decreasing to decreasing to increasing. So increase, decrease, decrease, increase. And every time you have one of these relative max or mins, it's going to cause that to change. So I want to look at some applications, and one such application of this kind of idea with increasing, decreasing, and maximums and minimums is the idea that I can maximize area. So I want to look at a problem where we maximize area. So there are 30 feet of dividers in a office space. And so we have a big office space, and we have 30 feet of dividers that we're going to divide one corner of our room. Okay, 30 feet of dividers. But I want to maximize the area that those dividers are going to encompass. Okay, I want the largest area possible for this square or rectangle or whatever it is. I want that largest amount of area, but I only have 30 feet of dividers to make the sides with. So if I'm thinking through this and I'm saying, I want to create the largest amount of area. Well, I don't know how much this side should be, right? I don't know, so I'm just going to let one side be x. But if I let one side be x, I do know this other piece. This other piece has to be the total amount of dividers in feet that we have minus how many feet I used on this side. So 30 minus x. And so this gives us two sides to some sort of rectangle square figure. But what were we looking for? What did I say at the beginning? We're looking to maximize, is it maximize? I don't know. I can't spell. Maximize area. Well, if we're going to maximize area of a rectangle square figure, we know that area is what? Length times width. Well, I have a length and a width. Perfect. So area is equal to 30 minus x times x. So what is that? So area is equal to 30x minus x squared. Now that we have this, what I want to do is I want to graph this on a graph. Okay. Okay, so I have, when I plug 5 in, I get 150 minus 25 is 125, and same thing for 25. 10 and 20 happen to be the same, and 15 happens to be at the top at 225. And so the maximum, we're looking for maximum area, so I want to know what's the maximum area. The maximum area is 225. Okay, that's my y. But what x value gave me the 225, and that would be 15. So my point, 15, 225, tells me two things: how long the sides have to be and what the area will be. So x is equal to 15, and the area is 225. Okay, and you can do this with any area maximization problem. It's really kind of cool. Now you can use a calculator, Desmos, whatever you want to graph this. Okay, so this is an example of a piecewise function. And piecewise functions are basically just functions that are multiple different functions put together to create one. And that's it. So I want to quickly look at how can I take this mess and put it on a graph. So it says x plus 1 occurs for values less than negative 2. Okay, so negative 2. Let's see, x plus 1. If I put in negative 3, because it's less than negative 2, that would be negative 2. So if I put in negative 3, I get negative 2. And if I put in negative 4, I would get negative 3. So it's a graph that looks like this, but it does not equal negative 2. It's everything less than negative 2, so even negative 2.00001, it still has to be defined there, but not at negative 2. So what I can do is I can draw an open circle at negative 2 and draw the line from there. Now, the middle piece says 5 from negative 2 to 3, but they're both equal to. So 1, 2, 3, 4, 5. Negative 2, filled in circle, and then it goes to 3. 1, 2, 3. So I have a constant at 5 from negative 2 to 3. So it's increasing, 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 jump, constant, and let's see what happens here. X squared. Well, it says bigger than 3, but I'm going to plug 3 in anyway. I may not have given myself enough space here, but I'll just do it in red. So at 3, 3 times 3 is 9. So at 9, I'm going to have an open circle. Then if I did 4, that would be 16, which would be somewhere up here. So it would be going like this through my functions. I should have done this beside instead of next to. But you can see there are 3 individual pieces. 3 individual pieces, but my function is all 3 of them put together. And that's all that a piecewise function is. It's just a function that has pieces. So we can use these in a lot of interesting ways to create some very interesting functions. And I do want to do one more example just to show some other things that can happen. So here's the other example. If I have a function that has open and it's going down, it's closed, and this one's open and it's closed. Now you know what? We'll make this open too. And then on the other side here, we have it just goes straight down. Okay? So there are 3 pieces to this. 3 pieces. The first piece is from here to here. Why did I put the parentheses there and the bracket here? Because parentheses is always open, bracket is always closed. Here, parentheses, parentheses. And here it's got an arrow. So there's nothing I really have to do. So let me put values to this and see if we can't create the pieces for each of these. Now we're not going to know what the specific function is, but we can write the intervals where they occur. So if I make this negative 1, 2, 3, 4, 5. So this first piece is from negative 5 to negative 2. So it's parentheses, negative 5, 2, bracket. This piece is defined for those x values. So but x less than 2. X between these two. Okay, what about the next piece? The next piece, this piece here, it starts at negative 2, so it would be parentheses, negative 2. It ends, we'll say that that's 1. So it ends at 1. This last piece starts at 1. Notice they're both parentheses, so they're both open, so they're both parentheses. This is parentheses because it's open. It starts at 1 and it goes to infinity. Now, the important thing, all of these are x values. I haven't talked about y yet. I haven't talked about what y does at any of these values. So, that's 2. So, let's mention real quick what happens at each of these places. Does y increase or decrease from negative 5 to 2? Well, y is moving down, so it decreases. Y is moving up, so it increases. Y is moving down, so it decreases. And so this is how we can combine the idea of increasing and decreasing with piecewise functions, is by looking at each individual piece and asking ourselves, well, where is it decreasing or increasing on the graph?